Okay, I gave you back, well, everyone except for Diana, I gave back the pages that you turned in yesterday. These are scanned and uploaded for grading, so the graded versions will show up with your lab stuff. But I figure I'd get them back to you now just because I at least think that this first page will be helpful to you in solving problems, preparing for the next exam, because the next exam will have our last dynamic stuff on it. I also, before I got onto the new topics, I wanted to finish out the thought. Remember, the end of lab, we kind of rushed it because we didn't have much time for this. So when I solved this problem, there were two ways I could solve it. First, which concept was involved in solving the problem of the race of the rolling objects? What was the concept? Rotational dynamics. How did you know it was rotational dynamics? Okay, it rolled, but there's one more thing than just rolling that was important to that identification. Well, down inclined plane is relevant. Well, if you expand on that, you get to the answer. It actually had friction. It was because the motion was changing. If the motion had been constant, it would have been an equilibrium problem. But the motion was changing, so it was a dynamics problem. So that's what made it rotational dynamics. Right, because as I emphasized yesterday, if you're not correctly identifying the concept, then the whole rest of the problem you're going to have difficulties with. So when it's a rotational dynamics, just like at this point with non-rotational dynamics, we have two methods of solving. What are the two methods of solving?
Work energy.
Okay, work energy or Newton's second law? That's ungraded, just to give you back the raw papers. So we can do it with work energy or using Newton's second law, both the rotational form and the linear form. Which method did I use?
Work energy.
I used work energy. Why?
Because it's
usually easier. I have one more question, and then I'm going to go ahead and show you what it's like to do it with the forces method, Newton's second law method. Russ, you had a question?
When is it not easier to use work energy?
That's actually a good question. Off the top of my head, I can't come up with an answer. So that tells you how often I try to use work energy if I can. Okay, my last question. I asked which one wins the race, but what did we solve for?
Final velocity.
The final velocity. Why did we solve for the final velocity when we're looking for who wins the race?
Because usually the fact that it's going faster.
It's going to go faster. It goes faster.
While what Russell said is true, we have to go to the limitation that we have applied for general physics. We're only dealing with constant acceleration situations. So if it's constant acceleration, then the one that is fastest at the end was fastest at all times, hence it covered the greatest ground in a given amount of time. So I used the final speed as a proxy to say who won the race, because it was constant acceleration. A place where Russell's idea would not work is if you were talking about, let's say, the race between the tortoise and the hare. At the finish line, which one's going fastest? The hare. But who wins? The tortoise. Why? Because they didn't have constant acceleration throughout. The tortoise had roughly constant acceleration of 0, going to constant velocity, whereas the hare was big acceleration, big acceleration. So that's where it would fail. But in our cases for general physics, it's not going to fail because we're limiting ourselves to constant acceleration. So now I'm going to show you how we would do this if we use the other method. So what's the first thing we do after we read the problem? We draw a diagram. So drawing a diagram, there's my ramp, which is randomly at 18 degrees. Here's horizontal. And here's the angle between the two. Then I have my object that's rolling up here. And if I'm going to use the Newton's second law, rotational and non-rotational equivalence, what do I need to add to my diagram? The forces. Right, we didn't do that with the work energy. But with the force method, we have to draw the forces, the free body, well, not just the free body diagram, but the forces where they act, because when you have torques, the where they act is an important aspect. So, what forces are acting on this object?
Gravity.
What direction is gravity point?
Down.
Down. Friction, what direction is friction going to point? Up the slope.
Yes.
We have to be specific because, of course, if you just say up by itself, it sounds like you're saying vertically up.
The normal force.
The normal force, in what direction is the normal force going to point?
Uh,
Normal to the surface, not opposite to gravity, but normal to the surface. One of these three forces I can write an equation for, and only one. Which one can I write an equation for? Force of gravity. Force of gravity is equal to mg. Why can I not write an equation for the force normal? I heard many words from Sarah and I couldn't make out any of them, so I'm just going to interpret for her. Because it's whatever's necessary to keep it from going through the surface. Whatever's necessary isn't an equation. Force of friction. Why can't I put an equation for the force of friction?
Because you don't know.
It's actually not that I don't know the coefficient. The problem specified it rolls without slipping.
Okay.
All that means then is that the force of friction is big enough to keep it from slipping. Remember, the force of static friction is always an equation that's inequality. It's less than or equal to a maximum value. And so I know we haven't exceeded the maximum, but I don't know what the maximum value is, and I really don't care. So that's all I can write is in terms of the values right off the bat. Now, you have everyone except for Judith has the thing I gave you yesterday. So if it's a rotational dynamics problem, what should I do next?
Define a point at the unknown to do the torque state. Or is that jumping ahead of the steps?
I don't remember what the order was. I had the steps, but just read. It's the bottom set.
After draw force diagram is apply sum of torques equals moment of inertia times A.
Okay, so let's do that. I'm just gonna follow the steps in that order, and then if it doesn't work out, then I'll say, well, maybe I didn't do a good job of writing the steps. So I'm gonna first apply some of the torques about where?
About the axis of rotation.
Axis of rotation. Where's this thing's axis of rotation?
Middle.
The center or middle of my rotational object, which is also the center of gravity. So some of the torques, I'm going to put A there so I can put some of the torques about A equals. And just like I said in lab yesterday, I'm going to show all of the forces, even though it's trivial. If I was going to do this just for my own, I would not show all of them. So we have three forces. Force of gravity. What's the perpendicular distance between the force of gravity and the center of mass / center of rotation? Anyone besides Sarah have an answer? Sorry, I don't mean to put you on the spot. I just want other people to think besides you.
Can you repeat the question in different words?
In different words. It's like we're at a spelling bee. What is remember, torque has an equation. I'm going to write the equation here. Torque equals R cross F. You have to put the vector signs or it means something different. And so if we want the magnitude of the torque, it's equal to R perpendicular times F or RF times sine of the angle between the two.
Okay.
So if my picture had been drawn accurately, the radius from the center to where the force acts would be vertical. What's the perpendicular distance between the center of rotation and where the force acts? Zero. It's zero. Because that force is going right through the center of rotation. And so I'd have 0 times force of gravity. Then let's go to force normal. What is the perpendicular distance between the radius vector that goes from the center to where force normal acts and force normal?
0.
0 again. Okay, so we're getting more in the swing of these zeros. I like zeros. And like I said, normally I wouldn't even put these in my equation, but I want to make sure people don't say, well, what happened to the normal force? We've accounted for it, it just gave us no torque. Okay, we have one final force, the force of friction, which is acting actually at the same location that the force normal was, the point of contact. What's its perpendicular distance?
90 degrees.
Okay, the angle is 90 degrees, which means the perpendicular distance is, well, the radius, whatever r is. Yeah, it's 1 times r. And so we're going to have r times the force of friction. What sign is that? Is that a positive or negative torque? Remember, r cross f, so my index finger needs to point from here to here. And then I orient my hand so my middle finger can point in the direction of force and my thumb points in, so it's negative.
Or can just like it was spin this way.
Or it's going to make it spin clockwise, which is negative. So that's a minus there. And what's the sum of the torques equal to? It's what? That's forces. Sum of the torques in equilibrium, it was 0, but this is dynamics. No, that's F, not torque. Moment of inertia times? Moment of inertia is the equivalent to mass. What's the equivalent to acceleration? Angular acceleration. Don't hate. I love this stuff. It's fun. It's like, well, I love doing puzzles. Maybe you don't love doing puzzles.
No, puzzles are.
All the pieces fit together. Sometimes it's hard to figure out. So this equation, summarizing it, minus r times force of friction equals I alpha. So I'll put a box around that because that's one of the steps. What's the next step then?
Apply some force equals MA.
Okay. Sum of the forces equals MA in each component direction. So if I'm going to do that, what do I have to do? Break forces into components. So now we get our table. I'm just going to do it below so I can, actually I'm going to shrink it down so I can see more. Make my table. X direction, Y direction, I have force normal, force friction, force gravity.
And do we want to tilt our coordinate plane?
That's a good question. Do we, everyone?
Actually, yes.
Yes. Because it's
accelerating.
accelerating. We want one coordinate direction parallel to the acceleration. Right? We've gone through a lot of these ideas and we're just, pull them out when it comes up. So my coordinate system is going to be like this. And so if I break those into the components, force normal. How much of force normal is parallel to my x direction? X. Force normal is in the y direction, so it's 0 in the x direction and all in the y direction. Force of friction, how much of the force of friction is in my x direction? All except for? It's negative. And I'm just going to put negative FF, okay? I'm not going to put mu something because we would have the inequality. It's less than or equal to mu whatever. How much of it is in the y direction then? Okay, then force of gravity. How much of the force of gravity is in the x direction?
Sine theta.
Okay, the people who said that are correct, but I'm going to show you why. Just, it's always, like if you're doing it on the test, you need to do it, right? So we draw our vector, magnitude of mg, parallel to the y-axis from one side, parallel to the x-axis from the other. So then the components are starting at the end, going to there, going to there. It makes a right triangle. And so we have the x component is that side, y component is this side. And so Which angle do we know? By methods we've talked about before, I know that's the angle. And so now we have the opposite side is FGX. So sine theta is equal to opposite over hypotenuse, which gives us, this is mg sine theta. And notice my arrow is in the positive x direction. So that's a positive mg sine theta. What about the y component?
Negative mg cosine theta.
Okay, negative because my arrow for FGY was down and to the left, whereas my arrow for y was up and to the right. And because it's the adjacent side, it's going to be mg cosine theta. Now what should we do now that we've broken into components?
Sum of the forces.
Sum of the forces. Which column do you want to sum?
Both of them.
Okay, I'm going to do y first. What's the acceleration in the y direction? 0. That's why we chose our orientation. And so that gives me n minus mg cosine theta equals 0, or n equals mg cosine theta. And then I have a really important question. Who cares? It's not part of this problem. I could do it. I can find the normal force, but it's not important to solve. It would be important if it asked about what the coefficient of friction needs to be to keep it from sliding. But it's not important to our question because it didn't ask that. We don't have to know what the coefficient of friction is. We just have it told to us that it's high enough. But now if we look at the sum of the forces in the x direction, that's equal to max. And we don't know what ax is. So I'm going to write this down and I'm going to get an equation. So I'm going to have minus force. I need to change colors. It's going to look like it's a continuation of another equation. Minus force of friction plus mg sine theta equals max. So there's a second equation. So I have two equations, the one that's got the blue box and the one that has the green box. You have a question?
So if our force of friction, and we know that it's not slipping, can we assume that the force of friction is 0 and get rid of that entirely?
No.
Okay.
If it would be sliding if force of friction was 0.
Okay, never mind. I was thinking correct.
Okay, what's our next step if you follow down the steps that I gave you?
Find the relationship between acceleration and angular acceleration.
Okay, find the relationship between acceleration and angular acceleration. We learned that the magnitude of that relationship is that angular acceleration is equal to the tangential acceleration divided by the radius. But that's a magnitude. We still need to worry about signs. Tangential acceleration is how quickly the edge is accelerating in a linear fashion. Or if we take, in this case, the edge is stationary, it's going to be how fast the center of mass is accelerating. That's the sense we're looking at. But if you look at the picture, if this accelerates in the positive x direction, what direction is the angular velocity increasing? Or we can ask this simpler, the angular velocity is increasing. What direction is the angular velocity going to be pointing if it's rolling down? If it's rolling down, is it rolling with a clockwise or counterclockwise rotation? Clockwise, is that positive or negative?
Negative.
That's negative. So the angular acceleration is going to be, it's increasing in the negative direction, so it's a negative angular acceleration. So a positive tangential acceleration in this picture correlates with the negative angular acceleration. So I have to throw in that negative side. That required just analytical thinking, right? It's not like this equation for the magnitudes is a given. But then determine if it has a plus sign or a minus sign, that's critical thinking only. So I have that relationship. What next?
Solve the equation.
Put them together and solve. So what am I looking for? I did say right at the outset what I was going to solve for.
find the velocity?
That's what I found before, but my goal this time was to find the acceleration. Once I find the acceleration, I can then calculate the velocity from that, so I can have a comparison to make sure I got the same answers from both. So I'm going to solve for the acceleration here, which is what you said, right? So I'm going to take my equations, and first I'm going to write the three equations together because they're too separated for me to see them all at once. So I had minus r, okay, make the colors match what they were before. Minus r force of friction equals I alpha, and then minus force of friction plus mg. I said I was going to match colors. That's not green, it turns out. And I'm going to change that tangential to an x. So I had those two equations, and then I put the black equation in to substitute for alpha, so I get it in terms of just my acceleration ax. So now I have to combine these. What's the easiest way you can think of to combine these two equations? I changed that to green, I swear I did. What's the easiest way to combine these?
Solve that for AX and substitute it for AX.
If I did that, I would be eliminating the variable I'm looking for. I would solve for the force of friction, which is not a problem. But that's going to take more steps because it's solving for the wrong variable first.
Shouldn't you just make it both equal to force of friction?
Okay, that's what I would do. I would take the blue equation. I'm giving myself some more room here so I can do it. I would take the blue equation and I would simply divide both sides by minus r, so that the blue equation becomes force friction equals I ax over r squared. Notice divide by minus r, the minus is canceled. And then I can just add these equations together. So I'll add the stuff on the left side together and add the stuff on the right side together. So on the left side, I'm going to have ff minus ff, subtracts out, eliminated. And I have mg sine theta on the left-hand side. On the right-hand side, I have I over r squared ax plus m ax, or factor out the ax. And I have ax times I over r squared plus m. So the final step then, ax is equal to mg sine theta over I over r squared plus m. Now, once again, I said ax will allow me to determine which one is going to win, because the one with the higher acceleration wins, because we have constant acceleration. So once again, the one with the smallest I is going to have the largest acceleration. We substitute in the i's, and we will get actually the same stuff there as we had in the denominator with our velocity equation. Now, one last thing calculationally, just to make sure that this fully agrees with what we did before. Let's go from this to calculate what the final speed would be. So how can I go from constant acceleration to final speed? What? An equation. Which kind of equation? A kinematic equation. Life sometimes makes you go back to the other areas in solving a problem. So the kinematic equation, I don't have time, I don't want time, so I'm going to use v final squared minus v initial squared is equal to 2ax delta x. And I want to find what the v final is, so I'm just going to put, what was v initial? Let's do the easy things first. What was the starting speed? 0. What's delta x? Delta x is the distance going down the slope. So delta x is going down the slope. What variable did we use yesterday? We used this y initial. So I'm going to need to relate delta x with y initial if I'm going to compare the two. So if y initial is the vertical part of a right triangle and delta x is the hypotenuse,
Why not over sine theta?
right. So we have delta x is this length here is equal to y0 divided by sine theta. Where did she get that from? Sine theta is opposite over hypotenuse. So sine theta is y0 over delta x. And so I'm actually going to write that down here, not just say it. So there's my delta x. So if I substitute in 2 times ax, that's mg sine theta over I over r squared plus m times delta x, which is y0 over sine theta. Then if I cancel my sine thetas, I have equals 2 mg y0 over I over r squared plus m is equal to v final squared. Square root both sides, and that's what we found yesterday. So we could have done it this way, but which way was more work? This way. That's why we did it the other way. So you can see, if you have choices, why it's usually easier to choose the work energy. Now, something I said last class period, we didn't have to do it this time. Why was no work done by the force of static friction here? It was not sliding. But what was the static friction doing? Okay, it was making it so it rolled, which meant that it was converting energy into rotational energy. If there was no static friction, there's no friction at all. It would have slid without rolling. It would have been all translational kinetic energy, no rotational kinetic energy. But if you transfer some of the energy into rotational kinetic energy, what is that going to have to do to the translational kinetic energy? You have this amount of energy. It was all translational, but now it's split, so this much translational and this much is rotational.
Don't you lose some of thermal?
Not here because we're not slipping. If we were slipping, we'd lose some of the thermal.
Can you clarify what you mean by slipping?
Slipping would be the ball or sphere or whatever sliding a little bit as it goes down, not just rolling.
Oh,
Right.
so like if you burn out.
Like so, if you burn out your tires, yeah, then you're slipping. So the friction is transferring energy into rotation, which is taking it away from kinetic, which means this kinetic is 1/2 mv squared. It's going slower because it's transferring energy into rotation. So when it gets to the bottom, it has the same total kinetic energy as it would have had with what we did before with no friction, but it's going slower because some of it's in rotation, some of it's in translation. Does everybody understand, A, that there are two methods? The steps, they brought us through, right? I didn't have to do anything tricky or different from the steps here. I just followed the steps one from another, and it just led me through to the answer. You're impressed?
I don't think I heard that one.
We have time. And you can see lots of practice like this if you look at the tutorials that I have on YouTube for you. Okay, in just a minute, we're going to come to doing a woo clap thing. So go, yeah. So go ahead and go there. Remember, you can text at PHYS151 to this number, or you can just go to www.wooclap.com/PHYS151, or you can take a picture of that code. And while I'm thinking about it, I didn't start up Woo Clap. I need to do that too. Woo Clap. I totally forgot to log in myself.
Also, did you get
No, I drove to Colorado and picked up my car because the Forerunner is Amy's car. Yes,
Well, that's what
and I have been driving Amy's old car, but I drove to Colorado and got my car, which is the Altima. Okay, going forward. And I actually wanted to start here. So we're starting to talk about fluids. And the first thing I need to talk about is states of matter. And go ahead. Okay. So states of matter, I will start with solids. Solids are things where the atoms are in fixed places. So we probably all learned in grade school that solids have the properties of fixed. What are the things that are fixed for a solid? Okay, the atoms have fixed locations, but that's not what you learned in grade school. What did you?
I learned the solid, liquids, and gases.
Yeah, I was like, that's about it.
Solids are locked
Not-
to each other.
In grade school, you didn't learn about the positions of the atoms, but you learned that solids have fixed. Go ahead.
Yeah.
In grade school. In grade school. Shape is one of them that you learned in grade school.
You don't know.
Fixed shape, and what's the other one?
AP kindergarten.
You're in AP kindergarten. They have a fixed shape and a fixed volume. Huh? Okay, well, my grade school science was very lame, and this is about all the stuff we learned in science in grade school. A solid has a fixed shape and a fixed volume. So that means that if I take a solid like this rod, it's, no matter what I do, unless I actually damage it, it's going to have the same volume and the same shape. Yes?
Is the story about the person with the crown in the bathtub true?
Archimedes, I don't know if it's true or not, so I say it's apocryphal, or it's a questionable truth. But it makes a good story that we're going to talk about. Okay, so a solid has fixed shape and volume. Now we're going to talk about the atoms a little, and we're saying, okay, the atoms themselves are in fixed positions. But if the temperature is anything above absolute zero, temperature is a measurement that's telling you about the average kinetic energy of the molecules. And so as the temperature goes up, the kinetic energy goes up, which means that they're vibrating more and more and more. So those atoms aren't perfectly fixed, but they're vibrating about a fixed location. But of course, if they vibrate, typically they're bouncing off of things. So let's just imagine these three students right here. They could just sit shoulder to shoulder and be happy if they're not moving about. But as soon as they start moving around, they're going to start spreading out, right?
Not really.
It's just get harder then. So when things heat up, they tend to expand a little because of them bouncing off each other and pushing each other away.
Are you saying what's expanding?
The spacing between you is expanding, Anna. I have to be careful here. Okay, so those are solids. If you keep going to higher temperature, the kinetic energy of the molecules increases until you reach the point that the molecules on the edge are going so fast that they can break the bonds that hold them. And so if they break the bonds, then you're not going to have it in its fixed position anymore. And of course, there's two things that could be going on. It could be melting, which is what we usually talk about, or it could be sublimating, which is going directly from a solid to a gas. Yes?
Does Brownian motion take place in solids as well as liquids, or just
We don't call it Brownian motion if it does.
what's it?
Hmm?
It's random motion.
Random motion works for me. A Brownian motion is talking about the motion in the liquid phase.
So it's only for liquids.
Right, because Brown was looking at pollen floating in water.
Right.
And then Einstein explained that that was because of the motion of the molecules of water hitting the pollens.
So why isn't it called motion in the other two?
Well,
Why do they have
the Brownian motion is the motion of pollen floating in water,
just palm?
as far as I know.
The erratic movement of microscopic particles in a fluid as a result of continuous bombardment from molecules of the surrounding fluid.
Okay, so I guess it doesn't have to be pollen, but that's what Brown observed was pollen. Russell,
Forgetting the state of matter.
excuse me?
You're forgetting the state of matter.
Forgetting the state of matter.
You're forgetting one of the states of matter.
Oh, no, I got that on the next slide. Don't worry. Okay, so he's probably thinking about astronomy. So then we have the liquid state. So this was solid. In the liquid state, you have the molecules are now free to move about, much like Southwest Airlines advertisements. But the molecules are still bound together by the substance. So the molecules can't leave the substance, but they can move around within. And so now, hopefully with the fixed shape and volume, it rings some bells. Do you remember what we said in grade school was fixed?
Isn't it volume?
Fixed volume is what we said in grade school for a liquid. Now, keep in mind what I just clarified for the solid. If the temperature goes up, they're moving fast, they bounce off each other and expand. So that's not perfectly true. The volume can change a little bit. And likewise for a solid, the shape can change if you stress it. Right? We learned about stress and strain. Nobody says this spring is no longer solid because you can stretch it. So there is some amount of change in shape and change in volume that can occur still within a solid. But it's very small generally, and so we consider it fixed. We consider the liquid a fixed volume, but it will fill whatever shape you put it in to within the limits of that volume. So if I take water and I put it in a cup, it'll fill the cup up to a certain level, whatever the shape of the cup is. But the molecules are still moving. What measurement tells us about how much kinetic energy the molecules have? Temperature. Now, it's not an exact equality. It depends on the material, what the relationship is. But the temperature is telling you about how fast they're moving. So if the temperature goes up, the molecules are moving faster. And these molecules, when they come to the surface, if they're going fast enough, they will have enough kinetic energy to break away from the surface. And what do we call it if the molecules break away from the fluid? I said fluid, I should say liquid. Evaporation is going into the gas phase. So if you heat it up high enough so that molecules have a kinetic energy that's larger than what we call the surface energy, the energy required to keep it in the material, then it will evaporate. And that brings us to the gas state, where it fills whatever shape you have and takes on whatever volume is available. So this classroom is filled with gas, air. Roughly 21% oxygen, 79% nitrogen. These molecules are just filling up the room. If we open the door, some will come in, some will go out, but as long as the doors are closed, they just fill this room. They take whatever shape and whatever volume is available to them. Some people might get all kinds of technical. If we were out in the, quote, vacuum of space, on average there might be one molecule in this room. Is a molecule of gas? Yes. Is it filling the space?
As much as
Over time, the answer is yes. At any instant, of course, it's not. But over time, it will fill the entire space. It just move around within it. So we would say, yes, it's filling the space. Okay, so these are the three primary states of matter, Russell. What other states of matter do we have? I have a number of them listed on the next slide. But let's just take answers from the audience before we go to the next slide. We have what?
What?
Plasma.
I said that.
I didn't hear you.
You coughed.
Okay, so we have plasma. What else do we have?
Not a clue.
Non-Newtonian fluids. I don't have that listed. Wait, what did you say?
Does count?
Not a clue.
Not a clue? That doesn't count.
Wait, so this count
I don't think that they fit in a special category.
Okay.
Any other states of matter besides
Wait, our question.
solid state, liquid,
The
and
12
plasma?
How are the 12 point? What state is 12 point in? somebody's in the 12th point, what state is it in?
It's superposition of all of them.
So is that one state, or is that something else?
No, it's just for all states.
No, it's the
Okay, no other answers.
Wait, there's.
He's looking them up.
Oh.
Okay, so let's look at what I have. I have plasma. A plasma is an ionized gas. So a plasma is an example of a gas, which some people get all holy and high and mighty and say, that's a different state. And other people, but it's still a gas state. But it acts differently. How does it act differently? Because you have the electron repulsion, or charge repulsion going on that you don't have in a neutral gas. So what is an example of a gas or a plasma? The sun. Instead of the sun is a massive incandescent, that's a gas. The sun is a miasma of incandescent plasma. Okay? Yes. There are two titles of songs that they might be giantly popular. I think they actually wrote the sun is a miasma of incandescent plasma. They took the sun as massive incandescent gas from nothing. And why did they do the second one? Because they got a lot of heat for people saying, no, it's a plasma, not a gas. Okay, then we have glass. A glass is an amorphous. You guys know these songs. Yes. I would join her, but we have to go home. Glass. Okay, a glass. A glass is an amorphous solid. Did you guys know that glass is not a normal solid? A normal solid is a crystalline solid, where each atom has a fixed location and it's repeatable. But glass is an amorphous solid, which means the positions are not repeatable. It's kind of random. I'm going to cover that. So, how do you make glass? Anyone have a clue? You heat sand up, and then what do you have to do?
Freeze it.
You have to freeze it rapidly. If you freeze it slowly, you're going to make quartz, a crystalline material, crystalline solid. But if you freeze it rapidly, you're going to make glass, an amorphous solid.
Like how high do you have to freeze that sand for glass to be?
How hot?
Yeah.
I don't know.
Like Colorado.
You just
It's like 1,000 degrees.
yeah, I mean, you look up the melting point of silica. I actually should know this because it's something that I have to cover in my physical science class, but I don't remember. So, glass is an amorphous solid, which means you don't have repeatable positions for the atoms. But otherwise, it's still a solid. Next, I have liquid crystals. Liquid crystals, well, those are like prevalent. The display of her iPhone, I believe, is still using the liquid crystal. So liquid crystals are these odd fluids that when you put voltages on them, they will change.
You said liquid crystal?
Yeah, liquid crystal.
Or LCD?
Excuse me?
LCD?
LCD is liquid crystal display.
Oh, that's.
Ooh.
Okay, so like,
That's what
when like lightning strikes sand or glass or whatever,
Yeah.
wouldn't that like take away that thing that says a non-crystalline solid because it's pulled rapidly from liquid? It's not, when it does that, it's not taking it from a liquid.
Yes, it is. The lightning strikes the energy of the lightning bolt, melts the sand, and then rapidly freezes. So it went from sand to liquid to glass.
Okay, okay. We learn something new every day.
That's why we come to physics class. Yes,
The
Ann.
heat point for that is 3,090 degrees.
2,000?
3,000.
3,009. And that's Celsius or?
We're Fahrenheit.
1,700.
Celsius is.
Okay, yeah.
Celsius
I was thinking it was,
Fahrenheit,
yeah. Because in science we use Celsius or Kelvin. And when you get up to a large number, there's nobody cares. If you're 1,300, you would care because that's 273. We don't use Fahrenheit. Old Georg made his scale, and his scale has been modified, so has the Celsius scale. And your Celsius scale, we'll learn, it's not what you think it is. The last one is a colloid. A colloid is the suspension of one material within another. So this here, anybody know what this is?
No.
You would. Oh, does it say, or did you know that? Oh, it says. Yeah, that's milk. Milk is water with little globules of butter fat that are suspended in it. It's a colloidal suspension, one material suspended in another. And that's considered another state. So these are all additional states of matter. And then we can go a step further. You guys probably know something really cool about water. What happens to water, what happens to ice when you compress it? It melts. Well, that's one of the phases of water. There's like 11 phases, or that's one of the phases of ice. There's like 11 or 12 phases of ice. So there's many different solid phases. What makes them different? Different positions of the atoms. Russell.
What's the name of the crystalline ice? The one that you did on the
Yeah, I don't know the difference in one from the next. Yes, okay, Oksana.
It wouldn't compress, like, if you use other, like, the same temperature, compress the water.
What?
Like, if you take another ice cube and another ice cube and seal another one, and then, like, you compress it, it will melt.
Well, it depends on your temperature, which phase you're in. If you're in the phase of ice that we normally deal with at atmospheric pressure and close to 0 Celsius, yes, it will melt. Russell?
It's called ice 7.
I7, okay. Okay, let's go to our woo clap question, which is, oh man, I'm going to start hating them for choosing that name now.
I mean, if it's like actually annoying, I can stop.
No.
I just think it's funny.
Okay, so here's our question, and take off the answers. Fluids are materials that flow. That is, they do not have a fixed shape. Which states of matter listed below fit the definition of fluids? You're answering more than one. So which ones of these will flow? Because that's our topic for this chapter is fluids. It's not solids, liquids, gases, it's fluids. Russell?
I mean, but if the gas is typically in the will it also flow?
If what?
If a gas is typically in the will it also flow?
No.
That's something for you to answer.
Because I mean, you can pull a couple.
Okay. Let's answer. We only have one answer so far.
You're welcome.
Thank you, David.
Aren't there 2 of them?
Hmm?
Am I right or wrong?
There are multiple answers.
It's trying to trick me
Wait,
up.
Dr. Webb,
Yeah.
question, is the glass referring to glass, like glass, or is it referring to like?
Glass like the glass in the window right there.
I'm not doing it. I'm not doing it.
Is there something different about like stained glass as opposed to like the glass that's typically used in windows?
There are lots of different recipes for glass with different properties. And to get stained glass, you're introducing dopants that absorb certain colors. So yeah, it's a different recipe.
They probably put that glass could be a fluid because there's the windows that like over time they do.
Okay, anybody still working on putting their answers in? We have 4 people who haven't answered, but I don't want to wait a long time because, oh, you can't vote anymore anyway. And I'm not going to extend it. I'm just going to go on. Except for, let's look at the results. 80% said colloids are fluids. Does milk flow? Can you pour it out of a pitcher? Yes. So that should be 100%. Colloids are fluids. The second one we can't read, but I really think it said gas. Because they're not benzoic. Can a gas flow? Yes. Yes, a gas can flow. It doesn't matter what temperature or what density, it'll still flow. So gases are fluids. What about glass?
Yes.
Okay, we have some confusion. 2 people said yes. Would you say that the window glass out there is flowing or not?
It's very slow.
Okay, very slowly. One physicist got really tired of people saying, oh, glass is a fluid. Well, they say glass is a liquid, like that's ridiculous. But they say glass is a fluid. So he wrote an article about this. And you know, people talk about if you go to an old, 200-year-old house or whatever on the prairies, you look at the windows, you see the ripples because the glass has been flowing. How many people have heard that? I've seen it. Okay, here's the truth. They put those glass panes in with lead. Lead flows much more readily than glass does. And so you would have had all of the lead flow out and the glass flow out of the window before you have any observable flowing of the glass.
So that's a no then, right?
So it's a no. The glass looks wavy because they didn't have the ability to make flat glass that we do today. They actually pour glass on top of water. That's how they get so flat. Okay, liquids. Do liquids flow? Absolutely.
No.
Liquid crystals. Yep, because they're liquid. They're called liquid because they flow. Plasmas, they're a type of gas, so they flow. Solids, everyone said no. Remember, lead is a solid and lead flows more than glass. But no, we still say it doesn't flow because it's so slow. So it kind of is a judgment call. Okay, we are out of time, so have a spadoinkle day.
Yes or no?